It says points R and T are each at a distance d from each of these two charges. One of them is positive, one of them is negative, and you can see that all these distances are d. The question is asking what is the work required to move a negative charge q from R to T, and here are your choices. Talk to a person next to you. You have 1 minute to answer this question. Alright, the correct answer here is 0. Why is the answer 0? Because you can see that the work done is nothing but the negative of the change in potential energy, which can be written as the Q0 times the change in potential. Q0 is the test charge. In this case it happens to be an electron. So the main thing is work done depends upon the change in potential energy, and which means it depends upon the change in potential. What is the change in potential from R to T? 0. Because you can see the potential at R, if you remember, potential at R is going to be K, you know, that plus Q, so KQ over the distance D plus K times minus Q over distance D, right? Because the potential at point R is being produced by both this positive charge and this negative charge, right? They are both producing. Similarly, the potential at T is being produced by this charge and this charge as well. So you can do the same. V sub T is KQ over D plus K minus Q over D. You can see the potentials are the same. In this case it happens to be 0 here and it happens to be 0 here. So there is no change in potential. Delta V is 0. Right? Delta V for us is nothing but, you know, you are moving it from R to T. So it's just nothing but Vt minus Vr. Okay, will your answer change if I had said this is not an electron that you're moving from R to T? No, it doesn't matter what charge you're moving from R to T. You know, so in other words, whatever is your Q0, the test charge, it doesn't really matter. So long as the change in potential is 0, you will have no work done. Right? The other thing is, what if I change the problem and I said both of these charges are positive? So this charge is positive and this charge is positive too. Does it matter? How many people think it matters? How many think it doesn't matter? The correct answer is it doesn't matter, because even if both charges were positive, you know, let's say that they were exactly the same, this will still be plus Q, right? So it doesn't matter. This is like 2KQ over D and this is 2KQ over D, so long as the change in potential is 0, which is 0 again, because they are the same potential, right? The work done is 0. So that's an important thing to know. What if this was plus Q1 and this was plus Q2? Will it matter still? No, it still wouldn't matter, because so long as these distances are the same, you can see that the potential that is produced over here and there will be the same, right? So the important thing here is, so long as VR and VT are the they turn out to be the same, Vt minus Vr is 0, and then the work done in moving a charge from T to R will be 0, or R to T will be 0. Okay, let's move on. It says a certain wire has a resistance R, another wire of the same material has half the length and half of the diameter of the first one. Resistance of the second wire is what? Please take 1 minute, talk to a person next to you. Time starts now. All right, so how are we going to do this problem? Remember, the resistance depends upon the resistivity of the material, the length of the wire, and the area of cross section, right? For a wire with a circular cross section, we can say that the area will be pi times r square. Is that making sense, folks? Yeah? Okay. Now, what happens in the second case? So R2 is such that we have the same material, that means the resistivity is the same, but we are given that the length is half, right? Length is half means we have L over 2. The area of cross section, what would happen? It says the diameter is half. The diameter is half means the radius is half. If the radius is half, you can see in the denominator here we have pi r over 2 square. Is everybody seeing rho? Instead of L, we have L over 2, and instead of pi r square, we have pi r over 2 square. So if we work through this, you can see that this is rho L, and do you see this is 2 square? So we have pi, then we have 2, and we have r square over 4. One of these 2's get cancelled, and so what we are left with is 2 rho L over r square times pi. So in other words, isn't this twice the old resistance? So this is equal to 2 times r. So the correct answer here is going to be D. Any questions about this? All right, let's move on. The third question is this. It says, which of the following copper conductors has the least resistance? And those are your choices. You have 1 minute to answer this. Please talk to a person next to you, and your time starts now. All right, so that's it, folks. Again, we are going to make use of the fact that resistance is rho L over A. So if we want the resistance to be least, so R is small if rho is small, right? And do you remember rho is small at high temperature or low temperature? Huh? No, because if you remember, resistivity at a temperature is equal to resistivity at a temperature T0, 1 plus alpha delta T, right? So as T increases, the resistivity increases. So if you want resistivity to be small because you want R to be small, that means you're talking about low temperature, right? So this means low temperature, right? So definitely cool. This means cool. So cool should be one of the things we should pick. Okay, it should be short. L should be small. Shouldn't it L be small? So L should be small. That means short. And what should happen to the radius? Should the radius be more? Yeah, because we want the area of cross section to be a lot. So that means we want it to be a thick wire. So A should be large. So that means the wire should be thick. So then the correct answer is cool, short, and thick. It's B. It looks like most of you got it right. That's great. Let's move on. Okay, here it says if the charge on a capacitor plate is kept fixed, but the air between the plates is replaced by a dielectric. Which of these choices is correct? Take a minute to talk to a person next to you. Your time starts now. All right, folks, that's it. Let's think about this together now. So let's say that we have, say, a parallel plate capacitor. So here we are told that we have fixed amount of charge. So Q is fixed. And now we are inserting a dielectric here between the plates of a capacitor, right? What do you think the dielectric does? Does it increase the capacitance? Yes. So we know that C with dielectric is always going to be more than C in vacuum or with air, if you like, right? This kappa is always greater than 1. You know, if we are taking anything other than vacuum, for vacuum or air, this is 1. All right, so if that's the case, we also know that Q is equal to C times V. If Q is fixed, if this is fixed and C increases, right, what we are saying is that C is going up. What should happen to V? It should go down, right, such that the product of the two stays constant. So in other words, here the potential difference between the plates decreases. That's the correct answer. Any questions about this, folks? Does that make sense? Okay, let's look at the next one. It says, two conducting spheres, one having twice the diameter of the other, are separated by a distance large compared to their diameters. Smaller sphere 1 has a charge Q and the other sphere 2 is uncharged. If the spheres are connected by a long thin wire, which of these is true? Talk to a person next to you. Your time starts now. All right, the correct answer here is A. The correct answer, folks, that's it. The correct answer is A, because what you have to remember is that in a conductor, very soon, in a very short amount of time, equilibrium will be established. And in equilibrium, the electric field everywhere inside the conductor becomes 0. And if the electric field everywhere inside the conductor is 0, that means the potential everywhere is the same. It's an equipotential surface. Conductor is an equipotential surface in equilibrium. So basically, it doesn't matter that you start out with, say, one conductor like this, then you have, say, some wire here, and then you connect it to another conductor like this. Is the whole thing now one conductor? Yes, once you connect, wire itself is a conductor. So now you should think of this thing as one conductor. And if it's one conductor, then the charges, even if you had charges on only one of these conductors initially, as soon as you connect it with this wire, very soon charges will redistribute themselves on the surface in such a way that the electric field, so charges will distribute themselves such that the electric field becomes 0 everywhere inside the conductor, including in the wire, inside the wire. That's also a conductor. And this means that the potential is the same everywhere. So if I go from here to here, I know that V final minus V initial, which is equal to negative of E dot dl. Remember we had learned this, going from the initial to final point. If the electric field everywhere is 0, if I go from here electric field is 0, here, then going from here to here, if this is my initial point and this is my final point, there should not be any change in potential. This is 0, right? The only way it can be 0 is if I go from here to here, the electric field is 0 everywhere. That means V final minus V initial is 0, and that means V final is equal to V initial. And that means the potential everywhere is the same. Whether I look at here, if I go from here to here, it doesn't matter. The electric field is 0 everywhere here. So integral E dot dl is 0. That means V final minus V initial is 0. That means the potential is the same. Is everybody clear on that? Okay, let's move on. This question says, if the electric field is in the positive x direction and has a magnitude given by E is equal to Cx, where C is a constant, electrical potential is given by which of these expressions? Talk to a person next to you. Your time starts now. Okay, we can make use of this relation, right? Do you see that we can make use of this? And if we make use of this, you can see that what we will get is that delta V is equal to minus integral E dot dl. In this case, it's a one-dimensional problem. The electric field only depends upon x coordinate and not on other things. So integral minus Cx dx, right? Let's say that we start from origin and we go to some value of x. So let's say we start at origin, we go to some value of x. So then the change in potential becomes minus C, and x integral x dx is x square over 2, right? So compared to origin, the potential, and at origin what will be the potential? 0, isn't it? X equal to 0 at the origin, so the potential at origin is 0. So compared to origin, any other place, we can find the potential at any other place, and delta V will turn out to be minus C x square over 2. Is this making sense, folks? So the correct answer here is E. Any questions about this? Is this clear? Okay, let's move on. It says, let Q denote charge, V denote potential difference, and U denote stored energy. Of these quantities, capacitors in series must have, you have 3 choices. Your time starts now. Talk to a person next to you. 15 more seconds, folks. 15 more seconds. All right, folks. So we have two capacitors in series, and you can see, let's say that this is the battery, and suppose this is the switch. As soon as you close the switch, what will happen? The electrons will start feeling a force in this direction, and electrons will start accumulating here. And where did they come from? They basically came from this plate, so equal amount of positive charges will be generated there. Now due to induction, on this side, even though this is insulator here, so these charges are not going to jump across, but what will happen is these negative charges will repel the electrons here, and they will come and accumulate here. Positive charges will accumulate here. So can everybody see that Q here and Q here will be the same? Plus Q minus Q plus Q minus Q. But if suppose this one has a capacitance C1 and this one has capacitance C2, will the potential V1 be different in general from the potential V2? Yes, in general all we can say is if the battery voltage, the potential difference across the battery is, let's say, E, then all we can say is that V1 plus V2 should be equal to E, right? We are assuming this is an ideal battery, it doesn't have any internal resistance, but V1 doesn't have to be equal to V2. In fact, we can tell this, Q should be equal to V1 C1, and Q should also be equal to V2 C2. But the point is the energy stored necessarily the same? No, because the energy stored in one capacitor, let's call it U1, this is the electrical energy stored in the first one, it can be written as half C1 V1 square. In the other one U2, it can be half C2 V2 square. There is no reason that these two things should be the same. So the only thing that is the same is Q. Any questions, folks? Anybody? Okay. Let's look at the last question. It is, for an ohmic substance, the electron drift velocity is proportional to which of the following? Talk to a person next to you. Your time starts now. All right, if you remember, we know that resistivity can be written as electric field divided by J. Right, do you remember this? Okay. Now, so from here, one thing we can see is that electric field and the current density are proportional to each other. Now, if you remember, the current density can be written in terms of drift speed, right? Do you remember that current density? J is equal to N E times the drift speed. What is N? N is the number of electrons, free electrons per unit volume. So different elements in the periodic table, for example, copper will have a different number of free electrons per unit volume depending upon its valency and things like that, how many total electrons it has, etc. Based upon all of that, you can figure out how many free electrons per unit volume will copper have versus zinc versus, say, sodium or potassium. All of these are different metals, but they all will have different N. All right. E is the charge of the electron. One electron, 1.6 times 10 power minus 19, right? Coulomb. And drift speed is Vd. So you can see that higher is the current density, higher will be the drift speed. If you apply a higher electric field, higher is the drift speed, higher is the current density, and higher is the drift speed. So E is proportional to Vd. Is everybody seeing that electric field is proportional to the drift speed? So you apply a higher electric field. In other words, for example, you use a battery which has a higher potential difference. That means you're applying a higher electric field. Do you think the electrons will drift at a higher speed? You bet they will, right? Is that clear to everybody? That if you apply a battery which has a higher potential difference, the electric field is higher, and that would mean that the electrons would be drifting faster. Please.
Couldn't it be A also, because J is equal to I over I?
No. What do you mean by cross-sectional area of the sample? The speed at which the electrons are the resistance will depend upon the cross-sectional area. You know, the resistance is rho L over A, right? So the resistance of the material will depend upon the cross-sectional area, but not the resistivity or not the drift speed or anything. You see? So drift speed, the thing is, if you look at this expression, suppose I give you copper wire, right? If I give you copper wire, and at a given temperature, copper wire, say at room temperature, at this temperature, you can go to a CRC table and find out what is rho for it, what is n for it, you know, how many electrons per unit volume. E is fixed, so you can see in that case E is proportional to drift speed, right? Please. Sorry, it is true that J is equal to I over A. So what does that mean?
J also equals n drift speed.
Well, okay, I don't want to confuse the matter more, but that's why I want you guys to, you know, the thing is, I've seen this in physics 1 also. No, I think this is an important thing, that when people are asked, for example, you know, F is equal to ma, does it mean that force depends upon mass? And nobody will say that will anybody say that the force on an object depends upon mass? No. But when you ask the same thing in this form, you know, when you say torque is equal to I alpha, and many times people don't understand, you know, they don't have a physical feel for what torque means, and then if the question is asking, does torque depend upon the moment of inertia? And obviously it doesn't, right? Do you see, if I'm applying a force on an object, you know, it's an external force that I am applying, right? It doesn't care about what the mass of the object is. It is true that mass will determine what its acceleration is, right? For a given force, mass will determine what its acceleration is. Is that making sense? But it doesn't mean that the force depends upon the, you know, mass of the object. So I think what depends upon what is something that one should be very careful about. Here, for example, I have often seen students in physics 1 say, for example, that torque does depend, you know, if the multiple choice question is asking torque on an object depends upon the moment of inertia, people are clicking yes, and the thing is, and the answer is no, because the thing is, moment of inertia is just like mass, torque is just like force. Moment of inertia will determine what the angular acceleration is given a particular torque, but torque is what you are, you know, is something that is external, right? So I think what is really the influence, and you know, what is determining what is something very important to keep in mind. So it is true that J is equal to I over A. It is also true that resistance can be written from Ohm's law, has another form which says R is equal to, it's also true that R is equal to V over I, right? Are both these statements of Ohm's law? They are, right? You can say resistivity is E over Ga, or you can say R is equal to V over I. They are both this one says V is equal to IR, this says E is equal to rho times J. Both of them are equivalent statements. And in fact, we obtained this by making use of the fact that we can write I is equal to J times A, and we can write V in terms of the electric field, right? Do you remember that we said that using this fact that delta V is equal to minus integral E dot dl from the initial to the final point, we can say if the electric field is constant, we can pull it out, integral dl will just become L, and so then electric field magnitude just became delta V over L. Putting the value of E here putting the value of J here, we were able to obtain this, right? And using this relation and using that R is equal to rho L over A. But the point that I'm trying to make is that in this equation, I'm free to write this. I'm free to write rho is equal to R A over L. But the question is, if in the exam you have a question that says, does rho depend upon the area of cross section? Does rho depend upon L? Or does rho depend upon R? You know, what is the question of does rho depend upon A or does rho depend upon L? Is the answer yes or no? The answer is no. Rho does not depend upon the area of cross section and rho doesn't depend upon L. R depends upon L and R depends upon the area of cross section and R depends upon this constant called rho that you can look up in a table. Just because I flip the equation doesn't mean that rho depends upon area of cross section and L. It doesn't. You have to understand which thing is the fundamental constant and which thing actually depends upon other things. So R depends upon the length. Longer the wire, more is the resistance. Thicker the wire, smaller is the resistance. But rho does not depend upon L or A. What, please?
So to clarify,
please.
fundamental constants are not dependent upon intrinsic properties.
Can you say one more time, please?
Fundamental constants are not dependent upon intrinsic properties.
Well, or rather, I would say that fundamental constants might only be dependent on, by fundamental constants, you mean how fundamental? For example, speed of light is a very fundamental constant, right?
I meant like resistivity and the drift velocity.
Okay, so I would say that resistivity and drift velocity are two very different kinds of things. So for example, resistivity, would you call it a fundamental thing for, say, copper? Yeah. So resistivity would be a fundamental thing for copper. So if I take a copper wire at a given temperature, say room temperature, its resistivity is something that I can look up in a table. That is it. So like you said, it is a fundamental constant for copper at a given temperature. On the other hand, the drift speed is not a fundamental constant. Drift speed, even in a copper wire at a given temperature, will depend upon what? The battery voltage. You know, which kind of battery am I using? That will determine what is the drift speed. If I push the electrons more, because my battery has a higher potential difference, that means it's exerting a greater force, the electrons will drift faster. So yes, I mean, I think, you know, you have to understand which things are constants for that particular case and which things depend upon the parameters. So for example, the drift speed, as he pointed out, is different from, say, rho, resistivity, because resistivity would be at a given temperature is a fixed thing for copper. All right. On the other hand, the drift speed will not be constant, because drift speed will depend upon what is the potential difference that I'm applying. You know, what is the battery that I'm using. Does that make sense? So think about it, because I think, you know, this is a very important point. What depends upon what? So it's, as I said here, it's clear here that acceleration, does acceleration depend upon both force and mass? Yes. Acceleration depends upon how much force I apply, and acceleration also depends upon the mass of the object. But force, does force depend upon mass? No. Force is what you are applying, you know. So if I apply a 3 Newton force, I'm applying a 3 Newton force regardless of what the mass of this object is, right? But it will determine whether this object will, how much acceleration this object will have will be determined by how much is the force and how much is its mass, right? Similarly, torque does not depend upon moment of inertia, right? But does angular acceleration depend upon both torque and moment of inertia? Yes. So if the torque, if you apply a particular torque, depending upon the moment of inertia of the object, the angular acceleration will be different. Does that make sense? So you have to think about which ones are things that don't depend upon other things and which ones do. Please.
Like, how do we know what depends on what?
That's what physics is about. That's why, you know, that's why when I'm teaching you systematically to reason through things, and I keep saying over and over again how things come about. For example, for resistivity, I showed you an expression even that showed that we derived an expression that shows that resistivity only depends upon the charge of the electron, the mass of the electron, the mean free time, tau, right? and n, the number of electrons per unit volume, and n or nothing else. In fact, we did a very fundamental derivation to show resistivity cannot depend upon anything. So if I ask you in the exam, does resistivity depend upon electric field? The answer is no. Why? Because if you increase the electric field, J will change in such a way that the ratio of the two is always constant, which is the resistivity, which is a fundamental thing of the material. And this is what physics is about. Reasoning through and thinking about, you know, what leads from what depends upon what and what doesn't. It's not about, you know, trying to memorize some, you know, formulas here and there, and that's why in fact all the formulas are given to you in the exam anyway. You have to reason about what does depend upon what doesn't depend upon what, and if you are having difficulty with any of these reasonings, please, you're very welcome to come and get help, but you know, do read through your things and try to reason through these things and make sure that you understand these relationships well. Okay? Any questions about this, folks? Okay. All right, so let's go over the rest of the practice test also. So here is the first question. The first question says, shown below is an electrical potential V plotted as a function of distance along the x-axis. What is the electric field at point 1 and in which direction does it point? What's the electric field at point 2 and in what direction does it point? What's the electric field at point 3 and in what direction does it point? Okay, what do you think, what concept do you think we should use in this case? Any thoughts, folks? Because you should have done this practice test at home. Anybody wants to share their thoughts on how we might, which concept should we use? Go ahead, folks. Anybody? Oh, you must have tried it at home, right? What concept would you use? Yeah, you can use the fact that using the fact that change in potential is this. Remember we showed, using that we showed, for example, that the x component of electric field is the partial derivative of V with respect to x, etc. You know, E sub y is minus dV dy, E sub, but here in fact you don't even have to worry about partial derivatives because there's only one direction. So you can think of it as a total derivative and that's just fine. Because x is the only direction that is relevant here, there's no y or z dependence. Does that make sense? So then, if that's the case, what would be the answer to part 1? Look at the curve. Let's look at the curve here. The curve is drawn, is something like this. You have x, which is in centimeters, and it looks something like this. And you're trying to plot the potential in volts. And you have some plot like this. You have something like this. You have something like this. You have something like this. Bless you. You have something like this. And you have something like this. Right? You have point A, point 1 right here. Let's first deal with point 1. So in order to find the electric field here, this is the plot of potential as a function of x, right? What we have to do is we have to take the derivative of the potential with respect to x. First of all, look at this slope here. Is this a positive slope? By the way, derivative is a slope, right? Is this a positive slope or a negative slope? Negative. This is a negative slope, right? So first of all, it's a negative slope, but then I also have a negative sign in here. So negative slope with a negative sign makes the electric field positive or negative? Positive. So that you know one thing, the direction of electric field at point 1 is definitely positive, right? Because dV over dx is negative because the slope is negative, but then there is also a minus sign. So minus sign with a negative slope, negative derivative, gives me a positive value. So one thing I know is that the direction of electric field only has x component, so we can even call it E if you like, is positive x direction. Okay, what about the magnitude? It's going to be the magnitude of electric field will be dV over dx, right? And I'm not going to write it as a partial. We can even write it, as I said, as a full derivative because of the fact that there is no y and z dependences here, right? If you want to write it as a partial, there's no problem. Please feel free. it's the same thing. So what is this thing? Anybody wants to tell me how to find the derivative? The easiest way to do, is this a straight line? So is the derivative of the slope or the slope constant? Yeah, so one way to do this will be, let's think about actually, we can draw a right angle triangle like this, and derivative dv over dx is nothing but delta v over delta x. Right? Is everybody seeing that? What is delta v? Delta v is this change in potential from here to here, and delta x is this. Look at your graph here. Your graph, if you look at your graph, you will see that this point here says plus 1 volt. This point here says minus 2 volt. So what is delta V, folks? 1 and then 2 and then 3. Isn't it 3 volt? Good. So this is 3 volt. And in the denominator, if you look to see how much is this thing, delta x. Delta x seems to be it's 1 centimeter, right? Do you see that it's 1 centimeter? Is everybody clear? Tell me that it's making sense that it's 1 centimeter. Okay, but 1 centimeter, if we are using SI unit, it will be minus 2 meter, and so this will be equal to 300 volts per meter. Okay, let's try. Is everybody clear about this? Huh? Or no? All we are doing, please. Oh, please come forward and take it. I brought some extra ones. You can even take a new formula sheet. I'll also give you the old formula sheet in the actual test. Okay, all right. Thank you so much. All right, so is everybody clear? By the way, could you have also done, let's say, for example, something smaller like this or smaller like this? It doesn't matter, so any delta V over delta X you do, so long as you're finding the slope of this line, you'll get the right answer, right? So choose whatever is convenient. Okay, what about at this point? Here is my point 2. What is the slope of this thing? What is delta V over delta X over here? 0. Is everybody seeing that this is a horizontal line? So delta V over delta X is 0 here, right? Slope here is 0, and so the electric field at point 2 is 0. So for part 2, E at point 2 is equal to 0. Why? Because delta V over delta X, is 0. I hope everybody understands that point. Okay, let's look at number 3, folks. So number 3 is a point over here. No talking. Okay, is the slope of this line positive or negative? Positive. So that means that dV over dx over there is positive, and that means the electric field will have a negative sign. So does everybody see that at point 3 the electric field will be pointing in the negative x direction, right? Because the sign will be negative. Okay, so at point 3, E is pointing in negative x direction. And what about its magnitude? So its magnitude will be, delta V over delta X. And again, can we easily find it? All we have to do to find the magnitude is again to look at what is this delta V from here to here, what is delta X? Isn't that true? Okay, what is delta V? Who wants to tell me from the plot what is delta V? If we take the whole thing. Yeah, can we suppose we take delta V to be 3 volts because we are taking it from the top here to the bottom here, okay? Then what is delta X? Does everybody see that delta X in this case is 0.5 centimeters? This thing is 0.5 centimeter. Look at your plot here. So if that is 0.5 centimeter, that is 0.5 times 10 power minus 2 meters, and this means this is 600 volts per meter. So you know the fact, would we have expected the electric field magnitude to be stronger here at this value of x compared to this value of x here? Why? Yeah, because the slope is steeper. I don't know if I drew it as well as it is in your practice test, but this slope is not as much. This slope is not as much as this slope. Does that make sense? Okay, let's move to the next question. Okay, it says, by the way, in the second question I forgot to give you an ammeter. There should have been an ammeter in the circuit. I'm sorry about that. So here is the thing. So in the next question, you have a situation like this. You have a capacitor and you have some ammeter over here. You have 3 capacitors. This is 1, this is 2, and this is 3. And all the capacitors have the same capacitance as C. And you have a battery. This is an ideal battery that's providing a potential difference of 4,000 volts. You have an ammeter in the circuit. There is a switch here that's initially open, and the question is asking you how many coulombs pass through the ammeter after the switch is closed, and what is the total energy stored in the capacitors after they are fully charged. And it's saying assume that the capacitors are initially uncharged. So as soon as we close the switch, what do you think will happen? You know, you can see that there's electrons that will start flowing. Here they'll go, some of them will go here, some of them will go here, some of them will go here. So the electrons will accumulate on these plates. Where are they coming from? They are coming from this direction, right? So what will happen on these plates? We will get equal amount of positive charges. Now here is the thing. In general, the capacitors in parallel, are those capacitors in parallel? Yeah, all 3 of them are. And capacitors in parallel in general have what the same? Potential difference. But you know, in this case it happens to be that they also have the same capacitances. In that case, would you also expect that they'll have the same amount of charge on them? Yeah, they will. By the way, one easy way to do this problem would be even to convert this thing into an equivalent circuit. If you convert it into an equivalent circuit, what will the circuit look like? What is the equivalent capacitance of these 3 capacitors? Will it be just 3 times C? Because remember, capacitors in parallel, they have capacitance equal to C1 plus C2, right? So in this case, 3 things are in parallel, so the capacitances will, the equivalent capacitance of this, this, and this will be C1 plus C2 plus C3. In this case, it's 3C. So if that's the case, can we easily figure out how much is the charge stored across each of them? How? Remember, Q is equal to C times V. This is V. And so we can say that Q is equal to C, which is 3 times this, times V, which is this. And we can plug in the values. C is given to us to be 25 microfarad. And E is given to us to be 4,000 volts. So Q turns out to be 75, well, okay, whatever. I mean 75 times 4 times 10 to the power minus 3 coulomb, right? Okay, great. Thank you. So that's the answer. What about the energy stored? Folks, let's move on to the next one. You can work that thing out, the numbers, but is that correct? So the next thing is, how much is the total energy stored? There are 2 ways to do it. one way you can do it is half C1 square V1 square plus half C2 square V2 square plus half C3 square V3 square. The other way to do it is just to say it's half C equivalent times V square, isn't it? Do you see how much is the total energy stored? Because the total energy stored, when you add up the energy stored in all of the capacitors, should be equal to the what? The total energy stored in the equivalent capacitor. So isn't it easier to just find the energy stored in the equivalent capacitor? Okay, so then U will be half C equivalent times V square, which is half times 3C times E square, half times 3 times 25 microfarad times 4000 volts, and this will be in joules. Thank you. Thanks a lot. Half C V square. Any questions about this, folks? Please. No, V is not equal to E, sorry about that. You know, I think this is a new notation again. So first of all, we changed the notation in the middle of somewhere, saying whenever we write V, we really mean delta V. Remember that was one thing I said to you. But now, when we were doing the last chapter, we also said that oftentimes you will see that they'll write it as a script E, because script E is a notation that is often called EMF, or electromotive force, and I think it's a very bad word, and it's a very bad because it gives you the wrong impression that it has something to do with force, but it's not, you know, it's not really, it doesn't even have the unit of force, it's really potential difference. So, but the thing is, I just wrote E because script E, because sometimes you will see that notation in the book, and I want you to be used to it, and it really just means EMF of the battery, which is really the potential difference across its terminal. And for an ideal battery, EMF, you know, is really just the voltage of the battery. But otherwise, if it's not an ideal battery, then EMF should be thought of as whatever is the potential difference when you have not connected it in a circuit. So if you take a 3-volt battery, its EMF is 3 volt. If you take a 6-volt battery, its EMF is 6 volt. But it's possible that if the battery is not new, when you use it in a circuit, its power output is not going to be what you expect it to be. Why? Because of that internal resistance. Remember, we said that when you're calculating the power output of a battery which has internal resistance, you have to be a little bit careful. Let me explain what I'm trying to say. So suppose this is not an ideal battery and it has some EMF, let's say it's 3 volts, right? Then I have to think about also some internal resistance. You know, let's say that this internal resistance is 0.1 ohm. I should think of this whole thing as being the inside of the battery. Maybe I have some other resistance here that I have put explicitly in the circuit, that is my resistance R, okay? I cannot do anything about this little resistance. Let me write it clearly, this R. And so in this case, what I'm saying, this is a non-ideal battery. And non-ideal battery is represented like this, with the battery with an internal resistance. And in this case, if I wanted to find the power output of a battery, if suppose, and you figure it out, what is the current in this circuit? Can you figure out the current? Yeah, you can use Kirchhoff's rule to figure out the current, right? You can go from here to here, here to here, it will be minus I times capital R, nothing here. Here to here, it will be plus 3 volts. Here to here, it will be minus I times small r, and that should add up to 0. And the thing is, and so power output in this case, usually the power output of a battery is E times I. But in this case, it's not going to be E times I, it will be E times I minus the power that is dissipated in the internal resistance of the battery itself. Right? And this much resistance the battery itself has inside it, you have not put it, so the power output is not going to be what you are expecting it to be, it will be different. Okay? And you have to really watch out for this I square times R. And you know, after some time, I told you already, if this I squared over times R becomes equal to E times I, is there any power output of this battery anymore? No, the battery is pretty much dead, you throw it out. Let's move on to the last question. It says nichrome heater dissipates 500 watt when the applied voltage is 110 volt and the wire temperature is 800 degrees Celsius. What would be the dissipation rate if the wire temperature were held at 200 degrees Celsius by immersing the wire in a bath of cooling oil? Assume that the applied potential difference remains the same, and alpha, the temperature coefficient of resistivity for nichrome at 800 degrees Celsius, is 4 times 10 power minus 4 per Kelvin. Okay? How can we do this? First of all, we know that the power dissipated so in this example, we know that the power dissipated for the hot case, remember the voltage is the same, will be V square divided by R of H. Remember, power can be written as I square times R or V square divided by R. Both are equivalent. Similarly, the power dissipated for the cold case will be V square divided by R cold. Isn't that true? By the way, you have been told that V is the same in both cases. Isn't that true? It says the battery voltage is the same in both cases. So that means we have V square is equal to PH times RH. And here we have V square is equal to PC, power when the thing is cold, times resistance when the thing is cold. So from both of these together, can we conclude that power when the thing is hot times resistance when the thing is hot should be equal to power when the thing is cold times resistance when the thing is cold? Right? Okay. Now, resistance when the thing is cold, can that be written in terms of resistance when the thing is cold? Sorry, when the resistance when the thing is hot, can it be written in terms of resistance when the thing is cold? It can't be, right? Because we know this. We know rho t is equal to rho t0, 1 plus alpha delta t. And you know, if I multiply by L over A, both sides, you see this becomes Rs of t is equal to Rs of t0, 1 plus alpha delta t. This is the resistance at some temperature T, this is the resistance at some temperature T0, and alpha is the temperature coefficient of resistivity, right? So then, using that fact, we can write here piece of H, and instead of R hot, can I write R hot is equal to R cold, 1 plus alpha times delta T? I can, right? So I have R cold, 1 plus alpha delta T is equal to PC RC. Is everybody with me? Piece of H, Rs of H is RC, 1 plus alpha delta T, PC RC. Can I divide by RC? Let's get rid of that. So what were we trying to find? Oh, we are trying to find PC in terms of pH. So you can see from here, PC is equal to pH, 1 plus alpha delta T. At this point, it's all plugging in the numbers. So everything is given to you. pH is given to you to be 500 watts. pH is 500 watts. 1 plus alpha is given to you to be 4 times 10 power minus 4 per Kelvin. And delta T is what? The change in temperature. And we are changing from 800 degrees to 200 degrees Celsius. So this is delta T. Please go ahead.
How did you get from RT equals RT initial to the next?
Sorry, are you asking how I got from this line to this line?
Yeah, like from the bottom right to the top left.
From here? Oh, I'm just saying that you can think of this as, if you like, you can call it hot and you can call this cold, right? This is just one temperature, so I'm saying this is R hot and this can be thought of as R cold. And so that's why instead of R hot here, I plugged in R cold 1 plus alpha delta T. Does that make sense? And if you are wondering, how I converted rho to R, all I did was I multiplied both sides of the equation by L over A, and you can see L rho H over A is Rs of H, and L rho sub c times divided by A is R sub c. Does that make sense? Right, so this thing is this thing is this. So I know R sub h is R sub c 1 plus alpha delta t. That's what I plugged in here. Is that making sense? Any other questions, folks? Anybody? So, okay, one thing that you should take note of here is that the unit over here said this is the alpha, this is the alpha 4 times 10 power minus 4 per Kelvin. And this is 800 minus 200 is the change in temperature in Celsius. Does it really matter that one thing is in Kelvin, one is thing? The good thing about, would it have mattered if one of them was in Fahrenheit and one of them was in Celsius? Yes, then it would have mattered, because Celsius scale and Kelvin scale have the same differences. You know, so a change of 1 degree in Kelvin, do you understand what I'm saying? So the differences are the same, whereas Fahrenheit scale doesn't have the same differences, you know. And so I think if it was Fahrenheit, you would have to be more careful. So I don't know if everybody is appreciating what my point is. What I'm saying is that this says per Kelvin, okay? And here you have delta T is equal to 800 minus 200, which is equal to 600, you know, degrees Celsius. You see, one of them is in per Kelvin, one of them is in, you know, change is in degrees Celsius. The point is that this is also, this thing can also be written as 4 times 10 to the power minus 4 per degree Celsius. Do you understand what I'm saying? Because the thing is, because the changes in Kelvin scale and changes in Celsius scales are proportional. Okay, that's what I'm saying. Anyway, I'm going to let you work out the numbers. Don't worry about it, please. Yeah, delta T is always final minus initial. That's a very good point. If we ever write delta V is also final minus initial. Delta T is always final minus initial. Delta U is always final minus initial. Please go ahead.
So the power dissipation when the temperature is cool be greater than the power dissipation when the temperature is hot?
No, the power dissipation. See, the power dissipation. You can see here. Yes, the power dissipation depends upon V square over R, right? So you can see that power dissipation, if the voltage is fixed, then yes, if it's higher resistance, then the power dissipation is less. If the voltage is fixed, if the resistance is less, then the power dissipation is more. The important thing is the voltage fixed or not? And in this case, it is. So let's look at this. Is everybody agreeing that if the voltage is kept fixed, right, then power dissipated is more when the resistance is less, right? In other words, PC times RC should be equal to PH times RH. Is everybody clear up to here? Great. Okay, then let's go to the next step. Is everybody agreeing that R sub H, resistance at higher temperature, should be 1 plus alpha delta T times R sub C? Okay, everybody agrees R sub C gets cancelled from both sides, right? We are going slowly over it. Tell me if at any step you see that there is a problem. So what we get then is PH times 1 plus alpha delta T is equal to PC. What you have to understand here is that PC is higher, greater than PH if RC is less than RH. Okay, so there is nothing wrong in anything that we have done so far. It's all very, you know, systematic. We went from here to here to here. Okay, now, so is everybody seeing all I have done is PC is equal to PH times 1 plus alpha delta T. If you like, let's even keep it on this side if it makes it look better. I've done nothing. All I've done is I've cancelled out RC from both sides. Go ahead, you were going to say something?
Is delta T positive or negative?
Okay, that's what I was trying to explain, and it's very easy to, in fact, if you think about it physically, it's trivial. you can immediately see whether delta T should be positive or negative. You tell me. If I say that R final is the hot thing, this is the hot thing, and R initial was the cold thing, would you expect the resistance for the hot thing to be more or less than the resistance for the cold? Tell me. Would you expect that hot thing should have more resistance? Remember we said that the resistance is due to the electrons colliding, resistivity is due to electrons colliding with the ions, and at a higher temperature the thermal vibrations are more. Because of that the electrons are more likely to run into ions, and if they are more likely to run into ions, the resistivity will increase as the temperature goes up, and if the resistivity goes up, resistance will go up also, because resistance does depend upon resistivity, right? So is everybody clear? So it's very easy to see that R sub H should be more than R sub C, right? Because this is higher temperature, this is lower temperature, and if R sub H is more than R sub C, does everybody see that this thing should be positive? It should be 1 plus something, right? Otherwise there's no way that the hotter thing will have more resistance than colder thing if this thing was not positive. So that means that immediately you can tell that delta T was really 800 minus 200, not 200 minus 800, otherwise that thing will be negative, and what you will end up with is that hotter thing has lower resistance. That doesn't make sense, right? And the point is that the PC is more, the power dissipated for the colder thing is more than the power dissipated for the hotter thing. And the thing is, why is that turning out to be the case? Can anybody tell me why is that turning out to be the case? Because that's a very good point. And in fact this is something you have seen before. Remember I was showing you those light bulbs in parallel? Go back to your notes on the day that I was showing you this. If you remember your notes, I was showing you this thing. These were two light bulbs. This had resistance, let's say this was 100 ohms, and this thing was R2, which was say 200 ohms. Do you know which one will be brighter? Tell me which one will be brighter, folks. Remember the power, see both of them, let's say this is a 9 volt battery, right? Do you see that the power dissipated in one is going to be V square over R1. The power dissipated here is going to be P2 is equal to V square over R2. So here this is going to be 9 volts square divided by 100, this many watts. Here this is going to be again 9 volts square divided by 200, this many watts. Which one is more? Is the power dissipated more in the 100 watt bulb? Sorry, is the power dissipated more in the resistance in the bulb which has a lower resistance of 100 ohms? It does, right? And that's exactly the situation here, because what you have to realize is that what we are holding constant is voltage. That would not be the case if we were holding what current, what constant? Folks, you have to really understand what is being held constant and what is not, because is everybody seeing that here voltage is being kept constant because this is in parallel with this and both of them have the same voltage as the voltage of the battery here, right? So voltage is being kept constant. In that case, lower resistance means higher power. So we have P1 greater than P2. Just look, in fact P1 is twice as great as P2, right? On the other hand, if I took exactly the same, exactly the two same light bulbs but connected them like this, what would happen then? I have this light bulb, this light bulb, this is R1 is equal to 100 ohms, R2 is equal to 200 ohms, and the question is which one is brighter? In other words, which one has a higher power dissipated? What is the answer? Because we have done all this in the context of actually looking at the demonstration, please. This time the one that has higher resistance will be brighter. Why? Because what is common for the two? Is the current common for the two? Yes. And so I squared times R, the power dissipated in this one, P1 will be I squared times R1. The power dissipated here, P2, will be I squared times R2. Right? Is I the same for both? Yes, I is absolutely the same. How do I know that? Because they are both in series. In fact, looking at this circuit, I can already tell you I will be equal to V divided by R1 plus R2. That will be 9 volts divided by 100 plus 200. This many amps, right? And this is the same exact current for both resistors, right? The same current is flowing through both, same I square. So you can see if R1 is smaller than R2, P1 is less than P2. This is not the situation here. This is the situation where V is the same. This is the situation like this one. Is everybody appreciating that when the voltage is kept fixed, in that case, the one with a lower resistance will have a higher power dissipated, just like in that case that we had discussed. But very good points. Everybody should understand this, because so it was very nice that that somebody brought this up. Please.
If you convert the delta T to Kelvin, do you get the wrong answer, or does that affect your answer?
No, and that's what I'm saying, that what I'm trying to say is what I'm trying to say is that if you convert this into Kelvin, so I'm saying that convert this into Kelvin and convert this into Kelvin. The differences are still going to be the same. You know why I'm saying that? Does everybody know what is the difference between Celsius scale and Kelvin scale? Tell me. So basically 0 degree Kelvin is minus negative. So basically we are saying that T in Kelvin is equal to T in the Celsius scale plus 273, right? So what would be this temperature? Tell me. T hot in Kelvin will be 800 plus 273 Kelvin. T cold in Kelvin will be 200 plus 273 Kelvin, right? Do you see when you plug this here, when you find delta T, do you see it's still going to be 600 Kelvin? Because why? Because this constant factor will cancel out. The proportionality is the same for Kelvin scale and Celsius scale, right? Is everybody clear on that? Any other question that I could answer for you? I did want to point out one thing. Have you ever looked at your electricity bill? How many people have looked at their electricity bill? I know that your mom and dad are probably doing it. Okay, a few people have. Do you know what is the unit that they use for how much energy you have used? Huh? No, the unit of energy is not watt. Watt is the unit of power, right? So energy per second. They are telling you this is your total bill. You have to pay. My gas bill comes out to $400 per month. Believe it or not. I mean, it's just incredible. But the question is, what is the unit that is listed there? The unit of energy that they use? Anybody? Go ahead. Very nice. Kilowatt hour. How many joules is a kilowatt hour? Let's try to see, because if it's a unit of energy, then it better be convertible into joules, right? So the power companies are usually using kilowatt hour because that is a convenient unit for them. So unit of energy used by power companies is kilowatt hour. Okay, go ahead. So who wants to tell me how will we convert it into joules? Kilowatt. How do we convert by the way, is it looking okay that it's the unit of energy? Yeah, because watt is a unit of power, so that's joules per second. And this will be joules per second divided by times time. Yeah, this is the unit of energy, right? Unit of power times unit of time is unit of energy, so that's great. Kilowatt, how many watts is that? 1000, thank you. Hour, how many seconds is that? Right, 1 hour is 60 minutes, and 60 minutes has 60 seconds, so this many seconds. So basically this is 36 times 1, 2, 3, 4, 5, 10 to the power 5 watt second. Is watt second joules? Yes, watt times second. So basically this is 36 times 10 power 5 joules. So the reason they don't send you electricity bills in joules is because you can see that number is going to be so huge. It'll be like in 10 power 5. So they don't like to do that. They would rather do it in kilowatt hours. Any questions, folks? Anybody? All right, please feel free to come individually with your questions and I'll be helping you out with those things. Now before we move on to magnetism, I had one more question for you. You know, this is a nice little thing that I wanted to show to you. Suppose if I had, remember last time we talked about a circuit with a capacitor and a resistor, let's say a light bulb. What do you think will happen to the light bulb in this circuit if the circuit looks like this? So I have a capacitor, I have a light bulb, which is, we are going to assume here is just an ohmic resistance, and this is a battery. I want all of you to talk to a person next to you and tell me, I'm going to catch one person and I want to know, as I close the switch, what do you think will happen to the brightness of this light bulb? You know, so you can say something like, well, it'll initially be very bright and then it'll dim, or it'll be initially dim and then it'll light up, something like that. Okay, or its brightness will stay the same all the time, whichever one. Please talk to a person next to you. So the question is, upon closing the switch, what happens to the brightness of this?
No, because it has to charge goes up, so it
Please. Yeah, capacitor is initially uncharged. All right, somebody from here, folks. Anybody from this side wants to share their thoughts? Go ahead, folks. It's a friendly class. Anybody wants to, please? Bright and dim. So he says initially it will be bright when you close the switch and then it will dim out. How many people agree with that? Okay, first of all, let's see if that's what happens. So here is your light bulb. Here's your capacitor. Let me close this switch and let's see what happens. Okay, watch. So he was right, right? So what he said is indeed what actually ended up happening. So the question is, how could he predict what would happen in this situation? So in order to predict what should happen, we have to think about the current, right? So let's say that, you know, we close the switch because we know the power dissipated here will be I squared times R. So when you close the switch, initially what ends up happening, the negative electrons start moving this way, right? So you have positives because electrons are moving away from there, they are going and accumulating here. They are moving from here, leaving behind positive, they are going, accumulating here. This is an insulator between the plates of a capacitor. So, you know, electrons can't jump from this side to this side, so that's why the positive charges are accumulating here because the electrons are leaving behind and electrons are accumulating here. Right, equal amount of electrons. So, so basically, as more and more charges accumulate, do you remember what happened to the current last time? Do you remember the current falls exponentially? Do you remember we found the current fell exponentially? If the current falls exponentially, wouldn't you expect that this thing, so basically, this thing was I is really equal to some I maximum times e to the power minus t over RC. So we can square that times R. In other words, and this thing is really, you know, I as a function of time. This is I0 e to the power minus t over R times C. And basically what we saw is that it fell exponentially like this. So if the current falls exponentially, wouldn't you expect that the power dissipated will fall exponentially also, and so the bulb will not be bright later? Okay, what do you think will happen if we have this situation? If we have a situation where we have a light bulb like this, you know, you have a resistor here and a capacitor here, and they are connected to a battery. Here is again a switch. Initially this thing is this capacitor is initially uncharged. This is some resistance R1, this is some resistance R2, but this is a light bulb. That's not a light bulb, that's just a resistance. If I close the switch, what happens to this light bulb? Does anybody want to say what happens? To the brightness. Again the same question. What happens to the brightness of this light bulb? Everybody should be talking to a person next to you, because that will help you. Talk to a person next to you. Again, think about what should happen. All right, any thoughts on what might happen to the brightness? Please go ahead.
It'll start off bright and then dim.
Okay, start off bright, then dim, and then how many people agree with him? So after you said it dims, then what did you say after that? Stay like that. Okay, so how many people agree? Let's try and see what really happens in this situation, and then we'll discuss why. So let's try. Okay, watch. This is the light bulb. This is a capacitor. This is a resistor. Let's look at this one. Okay, so you see what happens, right? Did you see what happens? Okay, but before we try to understand this, I wanted to ask you another question. In this parallel circuit here, suppose if I had this thing, suppose I had just two resistance, one of them is like one of them is R1 is equal to say 100 ohm, and the other one has no resistance. Let's say that, you know, R2 is equal to 0. You know, there's just a copper wire. That kind of a situation, do you know what it's called in common language? What am I doing? If I'm just connecting a copper wire from here to here, between these 2 points, do you know what in a common language it's called? Shorting or short circuiting, right? Am I not shorting those 2 points? Like I'm somehow just connecting a copper wire from here to here, there is no resistance in that part of the circuit. Do you know what will happen in this situation? Suppose I put an ammeter here, right, and an ammeter here. What do you think? And an ammeter here. What will those 3 ammeters read? Go ahead. First of all, tell me what will happen to the current here in this branch? Yeah, I thought you were wanting to answer this question. Anybody wants to answer what will happen to the current in the branch R1? Go ahead. There isn't any current. That's what shorting does. You know, like if you have a short circuit, you know what, there is no current flowing through this thing. So basically what has happened is, again, you know, think of this, think of the fact that this is not really 0, but this is almost 0. You know, the best way to think about it is think of this as 10 to the power say minus 10 ohms or something really tiny. Okay, because copper wire is never completely resistance-less, right? You're not talking about a superconductor or something. There's always going to be some teeny tiny resistance. So let's say that this is a very small resistance. Again, will it be true that if you think about the current here, I1, and the current in this branch, I2, is it true that I1 times R1 should be equal to I2 times R2? Because these two are in parallel, right? So I1 times R1 should be I2 times R2. In other words, you can see that I1, the current in this branch, should be I2 R2 divided by R1, right? So is everybody appreciating that the fact that we have R2 so small, almost 0, means that I1 is almost 0? So basically what I'm saying is if R2 is almost 0 because it's a short circuit, that means I1 is almost 0 too. That means there's no current flowing through the other parallel branches when there's a short circuit. And this is something that makes sense. The current always likes to flow from, take the path of least resistance, right? And so the thing is, here the resistance is pretty much 0 on this path, so all the current, if there is a current I here, all of that current will flow through this branch, and I1 will be pretty much 0. So I will really be roughly equal to I2, and I1 is roughly 0, right? Okay, now let's look at the circuit that we had here, that we were discussing. If there is very little resistance in this branch, and let's forget about the resistance of the capacitor, what happens to the current as soon as we close the switch, right? There is a current flowing here. Let's call this current I. So there is a current I flowing through the main battery. What will happen to this current I? It will split up into two parts, right? We can call it I1 and we can call it I2. Which way will most of the current flow initially? Look, there is almost 0 resistance in this branch compared to this branch. Do you see that this is almost no resistance because I haven't put an explicit resistor there in this branch? So wouldn't you expect that all of the current I pretty much will be I2 initially? Right? Almost everything will go through this, and that's why what he was saying initially is correct. And that's why initially it's as though this thing is not even there. So initially, if you wanted to calculate the current at time t equal to 0, suppose I want to know I at time t equal to 0, and t equal to 0 means when the switch was closed. Suppose I told you that this resistance R2 is 2 ohms, and let's say that I told you that this battery voltage is 9 volts. Can you tell me how much is the current at time t equal to 0 in this circuit, even if this thing was there? Let's say R1 is 1000 ohms. How much is the current? Folks, anybody? Initially at time t, as soon as I close this switch. Does everybody appreciate that at time t equal to 0, all of the current will pretty much flow through this path? This is like a short circuit, right? So this path will pretty much get shunted out. There is not going to be any current, as though this didn't even exist. Just like that up top one there. And because of that, how much is the total resistance in the circuit? Isn't this just a series circuit? Look at this. Right? Can we say that the current in this case is just going to be V divided by R1, R2? So this is 9 volt divided by 2 ohms. This many amperes. Oh my gosh, that's a huge current. Okay, it's not realistic, but we are just choosing some numbers. But you can see that this is the current at time t equal to 0 right after I close the switch. And so if I asked you how much is the power dissipated in this bulb, that's going to be that current square times R2. Right? Isn't that going to be a measure of the brightness of the bulb? Over time, what happens, folks, over here? As this current is flowing, basically what is happening is that electrons are going and they are accumulating here. Positive charges are leaving. So basically current is nothing but flow of electrons in this direction, and they are accumulating here. They are leaving behind positive, accumulating here, leaving behind positive. After some time, the capacitor will get completely charged, and the potential difference across the capacitor will become 9 volt. When this thing becomes 9 volt, the same as the battery voltage, what happens? Does the current stop flowing through this branch? So at some point this branch will become important because the current cannot flow through that branch anymore. There are enough negative charges accumulated that they exert equal amount of force to push the electrons back, so there is no current in this branch anymore. At that point, this branch will become important. Do you see that? And if this branch becomes important, after some time what will happen is that now it's like you don't have this, this has become unimportant. So as r goes to infinity, that means r is very large. Sorry, as t goes to infinity, I meant. As t goes to infinity, that means long time after switch is closed, what do you have? The current will become what, folks? Do you see the circuit has now become something like this, right? So the circuit starts looking something like you have a 9-volt battery and you have two resistors, R1 and R2. This might be 2 ohm, this might be R1 was how much? 1000 ohm. So what is the current in this case? Who wants to tell me how much is the current in the new situation long time after the switch is closed? Will it be V divided by R1 plus R2, because R1 and R2 are now in series with each other because the capacitor is just out. It's completely charged. There's no current flowing through that branch at all. So in this case, the current becomes 9 divided by 2 plus 1000 amps. And in this case, the power dissipated through this resistor, let's call this I nu. So the power dissipated will become I nu square times R 2. So this will be, I nu will be 9 divided by 2 plus 1000 square times R2, which is 2, this many watts, as opposed to in the previous case was this one, when you had this capacitor in the circuit. In this case, the power dissipated was, P old was 9 over 2 square times 2 watts. Do you see that this P old is a lot more than this P new? If the 1000 ohm is now important for the circuit, and because of that you can see that this thing is almost not bright. I mean, if you come close you will see a little bit if I shut the light. So it's not that there's no current flowing there, but there is current flowing, but now this resistor is actually important. The current is actually flowing through the resistor, through both resistors, not just the power, the light bulb, but also through this resistor, which has a very high resistance. Initially this resistance was not important. Initially it was going through this capacitor only, and in that case, since the total resistance in the circuit was low, current was more and this was much brighter. Does that make sense? So that's what, let me show you one more time. So it's bright, 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 it's less bright. So it's still, there is still a little bit of current, but you don't see the brightness as much because the current has become very small now, because the current is now this small. It's gotten reduced by this huge resistance, right? After this capacitor is fully charged, the current flows through this resistor. All right, any questions about this, folks? Anybody? Any other questions I can answer? Okay, so we are truly done with electricity at this point. So we'll talk about magnetism. Let me just again, and the thing that I wanted to show was these bar magnets. All of you are very familiar with these bar magnets, right? So one thing that you already know is that all magnets have two different kinds of poles, right? If one of them is north pole, the other one is south pole. All magnets will have a north and south pole. What happens when I bring the north pole of a magnet close to the south pole of the other magnet? They attract, right? On the other hand, if I bring the north pole of two magnets close to each other, they repel. What happens, what do you think happens? What is when I cut the magnet into two pieces? Do you know what will happen if I cut the magnet into two pieces? Huh? Yeah, it turns out that if you cut a magnet into two pieces, each of those smaller pieces will develop a north and a south and a north and a south pole. So each of those little pieces will itself be a magnet. What happens if you cut that little thing into two pieces again? It turns out that those little things will again become magnets. So, you know, they'll still develop a north and a south and a north and a south. And you keep cutting the magnets into smaller pieces, and it'll keep developing north and south, north and south. And what happens if you keep doing this, in the end all you're left with is one electron? Is the electron a magnet? The answer is yes. So the electron itself behaves as a magnet which has a north and a south pole. You know, so the magnetism of these bar magnets is due to, you might say, what is the origin of magnetism of this thing? Why does it behave magnetic? Why does it show this kind of behavior? And you know, if you bring this close to a magnetic material, something that is made of iron or cobalt or nickel, such as your fridge, somehow it sticks to it also, right? So the thing is, why does this magnet behave in such a strange manner? It turns out it has to do with something called the spin. Have people heard of this thing called spin? So it turns out that all fundamental particles have something called spin, angular momentum, or spin, just spin in short. And because of the spin, you know, so electron has a spin of a half. Each electron will have a spin of a half. And it's the spin of the electrons that causes this magnetic properties. Now you might say, oh, if the spin of the electron is what causes the magnetic property, how is that your eraser is not behaving magnetic? It's not a magnet, and this thing is behaving magnetic. Well, you're right. This thing also has a lot of electrons, and this thing has a lot of electrons, but this is not a magnet, and this is a magnet. And that is because somehow this piece of iron has been treated in such a way that the electron spins of different electrons have kind of lined up in a certain direction to give a net spin, you know, so that there is some kind of a net value left over. On the other hand, in this kind of a material that is not a magnet, you have the spin of the electrons pointing all in random directions. And in that case, there's no total spin or no total magnetic property here. Okay. Now why is it that, you know, somehow you are able to stick this thing onto the fridge? Because it turns out, even though your fridge is not magnetic, if you bring another iron piece to the fridge, it's not going to stick. So it's true that your fridge is not a magnet. Somehow it's actually going to start behaving magnetic when you bring a magnet close to it, right? Not another piece of iron. So somehow a piece of iron or a piece of cobalt or a piece of nickel has this property that if you bring it close to a magnet, the magnetic field produced by this magnet will cause the spins on the iron in the fridge to line up in a certain direction, and it will make it behave magnetic. All right, we'll talk about more of this next time. All the best, folks.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.